Um, I think we can just test out a couple of things. Firstly, you should see that this is recording. Secondly, I think you can just type in the chat something just to see that everyone can type, because I believe most people will be comfortable taking doubts on chat. Can someone type on the chat? I just want to check whether you guys are able to type on the chat or not. Cool. Thanks a lot. Yeah. Okay. So yeah, I got the setup to work, which is basically the tablet thing. It has a stylus, so it's very useful, especially when the topic we have, which is convex hull, is a very geometric / visual topic. Okay. Let's wait for 3-4 more minutes, 2 minutes more. I believe some people will join exactly on time. All right. I think we can start. So the topic is DP optimization for convex hull trick. It's a relatively advanced topic, so I would recommend everyone to like ask a lot of questions. Like if you have doubts at any place, just ask questions, because if you're seeing the technique for the first time, it is expected that like some things might not be intuitive in the first go. Second thing, I think a brief mention about me. My name is Sidhant. I've been doing comparative programming since like last 6-8 years or whatever, and I've been to the high school Olympiad thing as well as the university level ICPC World Finals. Yeah. So as we start, our motivation will be, we'll introduce a DP problem. We'll first cover the slow solution for that DP problem. Then we'll cover the idea for the fast solution, which is basically the convex hull trick. The most like the easiest or the most typical way to implement convex hull trick is through the stack idea. So we'll cover that, the implementation of that. And then we'll see a tougher problem, which actually requires a dynamic convex hull. And we'll discuss various implementations on how you can get the dynamic convex hull to work, which is like these 3 points in the thing. The different implementations. Then we have like additional problems which also use CHT. If time permits, we can go over them, and then that's all. Yeah. So first we go through the problem, which is called acquire. So the problem acquire, I think I found it on Spoj, and like it's present in like plenty of CHT related blog posts. So the problem is as follows. You have n rectangular plots that you want to buy, and n is big here. Like it's so big that you can't run n square, basically. That's the idea. Like n square is slow for this problem. And each plot has a width and a length. And a square unit of the plot costs you $1. You can buy a subset of plots in one go. And the subset that you buy, the price that you'll pay for this, that entire subset will be the length of the widest plot multiplied by the length of the longest plot. And you cannot rotate plots. So for example, if you have a 3x5 plot and a 5x3 plot and you're buying them in one group, then you'll actually be paying the max of the, whatever you want to call it, with the widths, which is 3 and 5's max, which is 5, and the maximum of length, which is 5 and 3, again 5. So you'll pay $25. You want to buy all the plots as your end goal, and you can purchase groups, and you want to minimize your total cost. Notice here, this language of this problem is like slightly, I would say, bad, in the sense that it says successive groups, but the order of the plots does not matter. You are allowed to pick this group, like 100,1 and 1,100 in one go, and 15,15 and 20,5 in another go. These can be your two groups. So your groups need not be contiguous in the order of the input. You can, so think about it more like subsets. You're picking disjoint subsets such that you pick all the plots. And for each subset, the cost you pay is the widest plot times the longest plot, like the widest width times the longest length is the cost you pay. So in this example, the way you come up with 500 is you pick 100,1 as a single group, 15,15 and 20,5 as one group, and 1,100 as one group. This one costs you 100. This one costs you 20 times 15, which is 300. And this one costs you 100. The sum of all these three is 500. Any doubts regarding this? Like just like going through the sample or the problem statement in itself. You could have bought in a different way. It's just that if you try out all the possible ways, you'll find that 500 is the cheapest. If you have any doubts, just like you can unmute yourself also, and you can also like just put it on the Zoom chat. Are you presenting something? I think my screen is being shared. Can other people see my screen? Cool. Yeah. So saying, yeah, I am sharing my screen on which I'm like scribbling over the slides. Yeah. So that's the acquired problem. Okay. So firstly, like, I mean, just once you look at the problem, I think the most non-trivial aspect of this right now is that if it's a DP problem indeed, then we are doing subsets right now. And in DP, typically you fix the order of something and then you do contiguous stuff. If you're doing subset, you'll run into bit masking issues or whatever, which is like high complexity. So these are the two observations in this particular DP problem. I'll just go over these observations. I mean, if you have time on your own, you can probably think about them more. These observations are not particularly relevant to convex hull trick. It's just for this problem, you need to apply these observations. The first one is there are some irrelevant rectangles. For example, if you have a rectangle of size, say 5,6 and another one of say 7,11, notice that you should always put your 5,6 plot in the same group as your 7,11 plot. Why? Because 5 is less than 7 and 6 is less than 11. So this plot is like strictly smaller than the other plot. So you will get this one for free if you group them together. So if a plot has both its width and length smaller than another plot, you just know for a fact that you won't pay for it, because you can, in whichever group the bigger plot is going, you'll just put it in there and you'll get it for free. Is this part clear? That there are some rectangles which we can just throw away because we know that there are some other rectangles which are strictly dominating them. So when those dominating rectangles, in whichever groups they go in, we'll just put these rectangles in that and we'll get them for free. So that's why you have some irrelevant rectangles. And now notice, like, now the other observation is basically, let's say we sort all the rectangles by width. I think in the implementation, they sort all of them by width. I just want to confirm. Yep, they sort all of them by width. So let's say we sort all the rectangles by width. Say we have these four only. 100,1, 15,15, 20,5, and 1,100. and this is the width, this is the length. So we sort them by width. So we get 1, 100 followed by 15, 15 followed by 20, 5 followed by 100, 1. Once you sort them by width, now just look at the lengths, which is like this value, this value, this value, this value. In this case, all these lengths are decreasing in order, which is like 100, 15, 5, 1. But say, for example, let me just manipulate the numbers a bit just to give you guys an idea. Say this was 20, 17, right? In this case, notice that these four values, 100, 15, 17, 1, when they come out in this order, you can notice that the widths are increasing, and these lengths should have been decreasing, but they're not decreasing because of this 15, 17 thing. So what do you notice? You notice that this 15 guy is actually irrelevant, because width-wise, this is smaller than this is smaller than this. And we also see that length-wise, 15 is smaller than 17. So this rectangle is completely irrelevant for us. We could have just dropped it. So the idea is that you sort them by one aspect, which is in this case width. You could have done it the other way around also, it doesn't matter. But you sort them by width, and then all the lengths should be decreasing in order. If they are not decreasing in order, you can just throw those rectangles in between which are not decreasing. So in this case, we could just throw away 15. Is this part clear? Because once you get this, you can argue that in the new thing, which is this excluding this guy, which is basically these three elements, 1, 100, 20, 17, and 100, 1. Oh, my bad. You could argue that you can always pick like segments of this thing. You need not go back to the original idea, which is that you'll pick a subset. You'll actually say that I can pick segments. So your first segment could be 1, 100. Your second segment could be these two things combined or some other way. But now you can create a DP out of it. I can formally prove why you can do the segment thing and like why you can argue that you don't need the subset thing. High level idea is, say you have rectangle 1, rectangle 2, up to say rectangle 6, and so on. It goes on till the nth rectangle. Say your current segment was this R2 to R6 in your optimal solution. So in your optimal solution, I'm referring to as the optimal solution. This was one segment, this was another segment, and so on. Now, proof by contradiction. Say someone comes in and says that, no, I know another optimal way to do this problem where I'll actually put R1 as one group. I'll put R2 to R3 as, say, a group. R4 will be its own group. And then this group itself will expand to R5 and R6. So basically, let me just label them in red. This entire portion is one group, and the remaining things are like just normal groups. And the person is arguing, like the proof by contradiction is that someone thinks that this is a better solution. Could it be the case? No. Why? Because if you're paying for this entire group from R2 to R3 and then R5 to R6, this entire thing, notice what's the maximum width. The maximum width is of R6. And what's the maximum length? The maximum length is of R2. So you're paying R6's width times R2's length for this entire group. Had you just put R4 inside this group, you would have gotten R4 for free, because R4's width is smaller than R6 width, and R4's length is also smaller than R2's length. So if you're picking a segment, it never makes sense to drop something from between that segment. You should pick a contiguous segment always. Does that make sense? You should never, like, it's strictly not optimal to drop something like R4 in between when you're picking a group. Is this part clear to everyone? Because like these two observations are pretty much what gives you the idea that you can sort by width, throw away the irrelevant rectangles, and then argue that you can do segment DP on it. Segment DP meaning like typical DP, that DPI denotes that I've processed all the rectangles from 1 to I, and what's the minimum cost that I've paid till now, which is like the most classical way of thinking about DP. Any doubts? Okay, I guess then we can move forward. So how does the recurrence, I mean, if you guys have any doubts, I'm pretty free. I can re-explain stuff. But like just understanding this thing is important because next we'll cover the recurrence itself, and like the entire trick comes on the recurrence. So in the slow solution, like, so we now kind of, after these two observations, we have this idea that we'll do contiguous segments once we've sorted by width and thrown away the irrelevant rectangles. So what will your DP look like? DPI is trying to denote what is the cheapest way to consume, I would use the word, but it's probably not the perfect word for this, to consume all rectangles from 1 to I. Right? That's what DPI tries to denote, that you have rectangle 1, rectangle 2, up to rectangle I. What's the cheapest way to consume all of them? And what's the recurrence for this? The recurrence is that you loop over J. So I'll just write it in a more, in a more latex manner in some way. And J is less than I. And then you say DPJ plus rectangle I. Let's say I'll use the more intuitive notation. Rectangle I is height times rectangle J plus 1 is width. Or maybe I can use the word length, but whatever, doesn't matter. Shouldn't it be rectangle I's width times rectangle J plus 1, because we have sorted by width? Probably correct. I'm just, yeah, let's just do that. I mean, Harry, you're probably correct. The thing that we have sorted by, which is the width, it should be that. Agreed. I'm just not sure in the input, how does it come? It comes like width comma height or height comma width, but the idea is correct. So let's just change it for here. What's like visually how you think about it is, let's say all of these were your rectangles. And let's say I label them, and let's say this guy is I, right? So the DP is basically saying that pick a J, let's say the J is this guy. Then you're saying everything up till here we'll consume via the DP, which is DPJ. Plus, we'll consume this as one group. And when we are consuming this as one group, notice for this group, what will be your cost? It will be the maximum width and the maximum height. Since we have sorted by, yeah, let me just fix it here also. Since we have sorted by width, so what will be the largest width here? It will be this guy's width, right? So Ri's width will be the longest width. And what will be the largest height? We know it's decreasing sequence because we have thrown away the irrelevant things. So it will be this guy's height. Right? So you multiply these two and you get the cost of this chunk. And you try each J because you don't know which chunk is best for you. Maybe it's this one, maybe it's a smaller one. And like the J comes till here, whatever. But you try each J, which is less than I. So that's why this recurrence, right? Now, if you run this DP naively, you can see you have n states to compute, and each state takes you order n time. And like this recurrence is pretty fast. You can just run this in O1, right? So the total thing takes you complexity n square. Any doubts regarding the slow solution of like how the slow solution works? And like, obviously, like eventually you'll print out DPN as your answer. DPN as your answer. Okay, Shreyas. Okay, I was asking any questions. Yeah, so you think there are no questions. Cool. So, okay, now we'll probably cover the convex hull idea here. So what's the convex hull idea? The convex hull idea is that you have a recurrence of the form where you depend, like you have your, okay, let me phrase it like this. So geometrically, when you're doing convex hull, you typically have like an x-axis, a y-axis, and a bunch of lines, right? And in this case, it's a minimum function. So we'll do min convex hull. And convex hull is basically based on lines. So let's say I have a line like this, which is called L1. And I have a line like this, which is called L2. Okay, it's actually the min hull. So I'll draw more other diagram. Like, let's say this is your line L1, and then this is your line L2, and then this is your line L3, and then This is your line L4. These are not line segments, so they are extending indefinitely. So they are going like this, whatever. I'm just not drawing them because in a convex hull, only like some parts are relevant to you, not the entire thing. The idea of a convex hull is that given a bunch of lines, in this case, L1, L2, L3, L4, and notice geometrically, what is a line? A line looks something of the sort y is equal to m1x plus c1. L2 looks like y is equal to m2x plus c2. I mean, this is like high school mathematics. You can read up on the internet or whatever that what's the most common way to represent a line. And here each line has a slope and a y-intercept. The slope is this guy, the m's, which is being multiplied by x, and the y-intercept is this c1, c2, blah, blah, blah. The intuition of c1, c2 is basically that if you feed x equals 0, that is on the x-axis, like this, x equals 0, where does the line hit the y? So here this will be c1. If you extend this, this will be c2, and so on. So these are the intercepts. So each line can be represented by two things, its slope and its intercept, right? And that's the equation of the line. So if you have a bunch of lines, the question in a convex hull trick is typically that I have a bunch of lines. For a given x, I want to find out which line gives me the smallest value. So say I have a specific x, say x equal 10. And my question is that which line gives me the smallest y for that x? So naively, what I'll do is I'll just plug in m1 times 10 plus c1, m2 times 10 plus c2, and so on. And I'll calculate the minimum of all these, right? But this is slow because if you have a lot of lines, say L1, L2 up to like LK or whatever, you'll spend order K time just feeding all the x's in, computing the answers and getting the min out of them. Notice in your recurrence, you're trying to do kind of a similar thing. You're trying to take min over a lot of things, and all of those things can be represented as lines. Why they can be represented as lines? Because you have a slope, which is this thing. That is, your slope looks like this. Your y-intercept looks like this. And your x looks like this. Just think about this. Don't think about the convex hull trick right now. Just think about it, how I'm framing the same question of this minimum thing in a geometric sense, that you have a bunch of lines and you're trying to minimize your y for a give, like out of all these lines for a given x. So in this case, I'm saying that if all your things which are less than I, that is, and you have constructed lines out of them, which is like L1 looks like R, whatever, like the slope of the jth line looks like this and the constant looks like this, and you're feeding in this particular x for all j less than I, trying to find out for which one do you get the minimum y. That answers your question, right? If we could do this thing fast, then we could calculate dpi fast. Instead of on, we could potentially do it in like o1 or o log n or whatever. Like answer this question, that if you have a bunch of lines L1, L2, L3, L4, and for a given x, I want to figure out which line gives me the smallest y if I feed that x in. How do I get this fast? Is this part clear? Like just the rephrasing of the original question in terms of lines. And you could construct all these lines. I mean, that's also another thing, because when you're calculating DPI, I'm assuming you're doing the iterative DP, not the recursive DP. You've already calculated the previous DPs. So you've calculated all the DPs from 1 to I minus 1. And since you have already calculated those DPs, you could have constructed the lines also, because you already know the DPs and you also knew the heights. So when you are trying to come to DPI to calculate it, by that time, you should have all those lines inserted in your magic data structure, which is basically the convex hull, right? Cool. So I hope this phrasing is clear. If you have any doubts at any point, just like put it on the chat or unmute yourself. So Okay, so how do we do this fast now? That's the question. Like, I mean, I just explained the naive way of thinking about convex hull, but like you actually do it fast, right? So for now, notice another thing in this problem, which is for this particular problem, this is true. Generically, it might not be true, which is notice how your slopes look like. Your slopes look like as follows. Mj is basically rj plus 1 dot h. And we already discussed that we have sorted our rectangles by their width. Right? So your slopes are decreasing in order, because think about this way. Your M1 will be R2's height, your M2 will be R3's height, and so on. Your MJ will be RJ plus 1's height. What's the pattern here? This value, M1 is greater than M2, M2 is greater than M3, so on, because your heights are decreasing. So all your slopes are decreasing. Geometrically, how does that look? Geometrically, it looks like as follows. Say your original thing comes in like this, your L1, because your slope is high. And then your L2 has a decreasing slope. And then your L3 has a more decreasing slope. And your L4 has a more decreasing slope. Right? And now notice why I always draw lines like these, because in this case, your minimum hull. So when you're talking about convex hull, at least from a DP optimization standpoint, you're always talking about like either the min hull or the max hull. In this case, we're interested in the min hull. Your min hull looks like this. Why? Because if I ask you for this x, say this is some particular x, say this is x equal 12, and I ask you which line gives you the minimum answer, you'll be like, definitely it's L2. Reason, we already see L1 is much higher. Like L1 comes here, L2 comes here. We also see L3 comes here. And we can, if we had extended L4, we'd see L4 comes here somewhere. So we know L2 is the smallest guy. So your min hull denotes, if you could store your min hull as like a bunch of line segments, you could say for a given x, just find that x on your min hull and you're done. You don't need to actually look at each line, evaluate that x for each line, figure out the y, take the minimums. You don't have to do all that stuff. If you have this this data structure which has these line segments, you could just, for that x, just look where you land and give that answer. Make sense? So, and the another interesting observation we got was that, so what sort of operations do we have to support? We have to support addition of a new line with this slope comma constant, where this is the slope, this is the constant, and queries. In a convex hull, you always have these two things that you want to do. As a data structure, you want to support two things: addition of new lines and querying. When I say querying, I mean for a given x, figure out what's the smallest value that the convex hull gives you. In this case, I'm generically talking about the min hull. You could argue symmetrically for the max hull if you wanted to. So two operations: inserting a line and querying. Right? And when you query for an x. When you insert for a slope comma constant. That's your interface generally that you're looking for in a convex hull. You want both these things to be fast. If you have these two things fast, I hope it's clear how you solve this problem. Once you calculate dpi, you'll insert a new line for the ith chi. So you'll insert mi comma ci, and then you'll go on to calculate dpi plus 1, where you'll call the query function with the changed x, and so on. So in this case, we noticed that your slopes were decreasing in order. Like your slopes were originally very high for L1, and then they were gradually decreasing. And you get this property because your slopes always look like this. And we know that the heights are decreasing in order. The benefit it gives you is you're always constructing your convex hull to the right. So say your L5 comes and it looks like this. Just like, I think I'll just clean up the diagram a bit so that it's more obvious. Yeah. So say your L5 comes and looks like, so it'll have even a more smaller slope, it could be a negative slope. That's allowed. Like it's not like the slopes always have to be zero. Generically, obviously, in this problem, you won't have negative slopes because the heights are always like non-negative, like positive. But generically, your heights can start, like your slopes can start going negative. So say you get a slope like this, right? It's the most negative slope out of all these because the direction of the line is like this. So that's your L5. In this particular case, notice your convex hull would have changed from the red line to the purple line, which looks like this. And your L4 would have just dropped out, and your L3 now cuts here instead of here. So, but like the general idea being that you're always just changing things on the right hand side. It could be this, or say, I'll just do another construction of L5 just to give you guys more ideas. Maybe your L5 doesn't look like this. Maybe your L5 actually looks like this, which is also allowed. I mean, depends on the y-intercept of L5. It could be the same slope, but just slightly offset to the right, looking like this, or it could be that slope. And both of them would give you potentially different convex hulls. In the first one, you'd get a convex hull like this. In the second one, you'd get a convex hull like this. Right? But always something to the right in general. So that's your stack approach, that L1 is on the stack, L2 is on the stack, L3 is on the stack, L4 is on the stack. Now you're adding a new line L5. It could be the case that L5 just comes in on the stack and comes to the right. That could be a possibility, say version 1. It could be another possibility that L1, L2, L3, and L4 gets kicked out actually of the stack, and you put L5. That's also a possibility. Another possibility could be that not just L4 gets kicked out, but L3 also gets kicked out. And so on. Basically, some elements from the top of the stack would get popped out, and then L5 would have been inserted. An example of how L3 could have been kicked out in this example would be, say your slope was even further to the left. That is the same slope, because notice my curvature of the drawing is almost the same. Like the slope is almost the same. I'm just playing with the y-intercept. They'll intercept this point. Whatever, this thing at different places. So I'm just playing with the C's, not with the slopes in themselves. Like I'm saying that it is possible to have the same slope, but different scenarios. Right. And in this case, your convex hull would have looked like, I'll just highlight it actually. Your convex hull would have looked like this, where you don't see L3 also anymore. Your L3 got popped out because L3's start point was here. L3 is completely redundant in a min hull that looks like this, the yellow shaded area. So everyone gets the generic idea that you have a stack where you're pushing lines in, and then based on some constraints, which we'll figure out, you pop some lines from the top of the stack and then push your new line that's coming in. I'll discuss the constraint on like the condition exact where you decide when do I pop off the stack something and when do I not pop off the stack. But is the high level idea clear? That you can think about how you want to place L5, but you'll always end up discarding things from the right only. It will never be the case that you just discarded L2 and you can put L5 in. That will never be the case. You'll either discard some suffix from L4 onwards, going to the left. Any doubts there? Cool. So, because there are no doubts, let's now discuss the condition exact. Like slightly tricky to erase. Let's say Okay. Yep. I think I like this construction now. Let's say L5 comes here. For now, let's cover L5 as this case. Okay, the most trivial case, L5 comes here. How will you decide that you not pop out L4? The way you decide it is you look at the second last element on the stack, which is L3, the last element on the stack, which is L4, and the new element being inserted. So L3 is your second last element, L4 is your last element, and the new thing being inserted is L5. What you compare is where do L3 and L4 intersect and where do L3 and L5 intersect. So you're comparing two intersection points, L3 comma L4's intersection point and L3 comma L5's intersection point. Notice here L3 comma L4 intersect here and L3 comma L5 intersect here because your L3 is actually a line going till here, right? Since the intersection is to the right of L3 comma L5, you'll be like that L5 will remain. It just gets pushed in. It's not like it doesn't pop anything. But take the other example, which is like the more interesting example, I'd say, where your L5 is actually coming in here, right? In this case, notice what happens. You again calculate L3, L4's intersection, which is here, L3, L5's intersection, which is here. If you look at from an X coordinate perspective, which one has a smaller X, like which one happens first when you look at from left to right? The L3, L5 intersection happens first. Because it happens first, you know that L4 is now wasted because it happens at the right, like L3 and L4's intersection happens towards the right. So the entire L4 chunk is useless for us. And this is a pretty strong statement to make. We are saying that L4 as a line will never be part of our convex hull in any way. So just discard that line altogether. So that's why we can pop it from the stack. And we just don't push L5 in yet. We just don't do that yet. We check the new second last, and the new thing coming in. So now we check. So now notice once you've popped off L4 from the stack, what's your second last and last thing on the stack? The second last thing is L2, the last thing is L3, and the new thing being inserted that we're trying to insert is L5. So we try to do the same thing, comparing L2, L3, and L5, where we say, with respect to L2, where does L3 intersect? So we change our comparisons that we are trying to figure out. L2 being intersected with L3, where does it happen? And L2 being intersected with L5, where does this happen? So we notice L2's intersection with L3 happens here, and L2's intersection with L5 happens somewhere here, right? If you extend L2 and L5 goes like this, so this happens here. So since the new intersection happens to the right, it does not discard L3. Think about it carefully. It does not discard L3 because the new intersection happens to the right. That is, L3 still remains useful. Because L3 remains useful, we'll not pop L3 and we'll just push L5 and we're done. But had it been the case that L5 was even more to the left, my bad. Like, had it been the case that L5 looked like this, right? In that case, notice your L2, L3 intersection will still be this, but your L2, L5 intersection would be here. And when you go from left to right, you'll see that L2, L5 intersection happens before L2, L3 intersection. So I'll discard L3 because now I know for a fact that L3 is also useless. So I would have discarded L3 as well. And then again, I would have compared the second last thing, the last thing, and the new thing being added. And I keep doing that in the stack. Obviously, if you only have like the last two elements or whatever, you'll just push this in. Like once the stack size reaches 1, you'll just say that add the new line in. Don't think about it. But till the time the stack size is at least 2, you'll always compare the last, the second last, and the new thing being inserted and decide whether the last thing that was inserted is relevant to us anymore or not. Based on this intersection condition, that does the new thing happen to the right or does that happen to the left? Is this part clear? Because this is pretty much the crux of the implementation. Like after this, it's pretty simple. You just work out the math of like where the intersection point happens and then you just decide based on that when you're popping from the stack or when you're not popping from the stack. If anyone wants me to go over like some parts of this again, just let me know. Cool. So I'm assuming this is clear. So moving to the implementation in this problem, you, for some reason, I just copied off the code from the WCAPG website and just like put screenshots of it. They are not using the variable C, they're using the variable B, but it means the same thing. It holds the y-intercepts. So their sentence for line equation is basically y is equal to mx plus b. Weird, but yeah, that's their notation. So they create two vectors. You could have created a pair of vectors. I mean, it's pretty much the same thing. Nobody cares. But yeah, they create two vectors, m and b. That's the main thing. In their main function, they take in all the rectangles in the A array here. They're just inputting all the rectangles. Then they're sorting it by whatever they say by height. But for our sake, let's just call the first thing as width because that's how intuitively we thought about the entire thing. And let's just call the second thing as height. It doesn't really matter. It's symmetrical, like the entire problem for us. And then once you've sorted all the rectangles, you just loop over them. And in your rectangle array, put all the relevant rectangles, the useful rectangles. That is, so you basically have this condition check that if the height of the n equals 0, if the height of the previous thing is smaller than the height of the new thing, then you yeah, so you keep on running this loop to kind of throw away the irrelevant rectangles. You're decrementing your n each time. And yep, so originally your n is 0, so you won't run this loop at all. You'll just put the first rectangle in. In the second iteration, you'll be like, I'll discard anything before me if it's supposed to be discarded. So you'll put the first rectangle in your rectangle array, that is R1. Then maybe you put your second rectangle in. Then when you're putting the third rectangle in, maybe you realize that, oh, this R2's height was actually smaller than my height. Its height is say 7. And the R3 coming in has a height, say 10. In that case, you know that this R2 is pretty irrelevant for us because even its width is smaller because it's sorted by width and its height is smaller. So just throw it away. And that throwing away part happens like n minus minus. So you decrement your counter and you overwrite on that thing, which happens here. So TLDR, eventually you end up with this rectangle array, which is the useful array, which only has the relevant rectangle. So this rectangle array has two properties. The widths are sorted in ascending order and the heights are sorted in descending order. The widths are sorted in ascending order just because of the sort statement, and the heights are sorted in descending order because of this constraint that we are running. Right. And then, as I explained earlier, you have this interface in your convex hull, which is addition of a line and querying. In your addition, you'll provide the slope and the constant. Notice what's the slope that we discussed. In our implementation, we discussed our slope will be the height of the next thing, and our constant will be the dp. So originally they had the first thing, the height of the first thing, which is the 0th thing, and the dp, which is 0. And in subsequent iterations, they add the height of the next thing and the dp. They are not storing the dp in an array, they are just storing it in a temp variable called cost each time. So, but this is actually dp of, I'd say, I. So each time they're adding this as your constant and this as your slope, which is like in our language, it's ri plus 1 dot h. right? So these are the slopes that are these are the lines that are being added. And each time you're querying what? To calculate a DP, we said we'll query for this. Our X will be the width of the current guide. And we are querying on the previous lines inserted. So we haven't inserted the current line yet. So that's why the add happens after we have queried. We first query on the current width, which is ri.w. So that's why the query happened on ri.w. Whatever we get, that's your DPI. And then you use your DPI to add it for the, add that as a line in the data structure. And eventually you just print out the last cost, which is DPN. So that's the high level solution. Notice in pretty much all the HT trick questions, you're essentially going to exploit this interface of insert/add and then query. That's the general idea. So if you're maintaining a code book or something of that sort, you'll be more interested in the insert and query methods and just writing them down correctly. And then for a given use case, you could just play around. Let's go through the add first. I would say this is the add method. So you're adding a slope and a constant. You push back the slope, you push back the constant. Notice these are vectors. They are not actually stacks. The reason just being that you want to, in this particular implementation at least, you want to access the last as well as the second last element of the stack. If you're trying to access the second last element of a stack, it's kind of non-trivial to do it via the STD stack implementation, because you'll be popping out the last element, then looking at the top, and then figuring out the second last element. In a vector, it's easy. You can just look at the second last element. The interface provides you with that support that you can look at. You can random access a position. In a stack, you can only look at the top. You can't look at behind it. So your condition is as follows. If the stack is of size greater or equal 3, and the second last thing, the last thing, the new thing I inserted, this is the second last thing that I was talking about. This is the last thing. And this is the new thing. That is basically the thing that we inserted just now. Right? Between these three things, if it's bad, what we mean by the bad method, that the last thing is actually useless. The new thing is definitely going to be useful because the slopes are decreasing in order. The new thing will become part of the hull for sure. But the last thing might be relevant. So if it's bad, that is, if the last thing is bad, then you remove the last thing. So that's why we erase the last thing out. And your bad is basically a Boolean method, which just tries to figure out is the intersection point of the new thing. So it uses this notation of L1, L2, L3, basically saying that this was your L1, this was your L2, and this was your L3. If your L1, L3's intersection happens to the left of L1, L2's intersection, then you return true. In this case, we would have returned a false. But take another case, say like this, we would have returned a true saying that L2 is actually bad. L2 happens actually to the right. So you're basically testing this condition. And the way you test this condition is, you can work out the math. I'm not going to do that over here, but the intersection of L1, L2 happens at this X coordinate. And the intersection of L1, L3 happens as this X coordinate. And what you want to compare is L1, L3's intersection happening to the left of L1, L2's intersection? So L1, L3's intersection, that is this statement, that is B1 minus B3 divided by M3 minus M1, happening to the left of B1 minus B2 divided by M2 minus M1. You just cross multiply this. You don't want to do divisions in your code if you're just looking for a comparison. In this case, you're just looking whether this happens to the left or not. Yes or no question, right? You don't actually care about the coordinate, the X coordinate itself. Calculating that X coordinate is not really important here. It's more important that which one happens first, like which one is the smaller value. So in that case, you don't really want to deal with doubles. You want to be as precise as possible. So you just cross multiply. So you get the equation B1 minus B3, M2 minus M1 being compared with B1 minus B2 times M3 minus M1. You could have just run this. For some reason in this implementation, they multiply this thing with a -1, 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 which basically does nothing. I mean, so they just flip this around, which is B3 minus B1. They flip this around, which is M1 minus M2. They flip this around, which is B2 minus B1. And they flip this around, which is M1 minus M3. I don't know why they do that in this implementation, but it's the same thing. And if this is less than this, which is basically that this, oh my God. If L1, L3 intersection did indeed happen before L1, L2 intersection, this is basically L1, L3 intersection happened before L1, L2 intersection, then we return true saying discard L2. That's what it means, right? When we return true, we are basically saying that discard L2. L2 is not useful to us. And we keep on doing that for the second last, last, and the new thing each time. A pop question here, pop quiz question. What is the time complexity of this erase? In an STD vector, when you are erasing something, you're not erasing the last element, you are erasing the second last element. Is it a O1 operation or is it a ON operation? Like what sort of big O are we expecting for T-Rex? You can just, like, if someone has any ideas or whatever, you can just put it on the chat. What, like, how slow is this operation running when you are erasing the second last element from a vector? Yeah, so Hari is correct. That this is actually O1. So it's not a case of worry. I'm just trying to get people on the same page that don't think of this as a slow thing. I mean, it is slightly slower than, like, say, a stack pop or whatever, because you are in, like, however the erase implementation works of a vector, it will try to, like, slide the last element one step to the back, but it's not significantly slow. It's still in the big O1 frame of mind. So it's a good implementation as such. So that's the implementation idea. And generically speaking, okay, sorry, I haven't covered the query yet, but this was the insert method, right? So just to maintain the stack, we keep on popping stuff and throwing out the bad things. And we have already inserted the good thing in because we know for a fact that this thing goes in. What about the query method? Okay, so for query, I did not explain it fully yet, but in this particular question, which is not generically true, your queries are of the form x equal ri dot w, right? So you're querying in the first iteration, you'll be querying for x1 equal r1 dot w. In the second iteration for r2's width, and so on. Notice you'll be querying increasing x's because your widths are increasing, because you sorted by widths. This is just a coincidence in this particular question. It might not be the case in every convex hull trick question you see. But because this is the case, that you're getting this property for free, that you're querying always in increasing x's, you can notice how your queries look like on the geometric hull. Maybe your first query is here, right? Then maybe your second query is somewhere to the right. Then maybe your third query is somewhere to the more right. What you could do is you could do a pointer approach or a sliding window, whatever you want to call it, pointer approach on the convex hull. That originally my x1 is being catered by the line L1. Then my x2 might be catered by the line L1, if not maybe by L2. And so on. You always keep on moving to the right in your line segments that you're looking at. You get this property for free because you're increasing in x's in your query. Had your x's been in arbitrary order, which is that your x1 is here, your x2 is here, which is somewhere to the right, and then someone queries somewhere x3 in the middle, because, like, just because of the pattern of the problem, you're querying randomly. In that case, you don't get any such property. You won't start sliding, because then you could have wasted a lot of time coming back from x2 to x3. You don't get any amortized complexity benefits, right? In that case, you just binary search for each x. So you'd waste log n time for each insert. Sorry, for each query. When I say binary search, I basically mean that you have this stack, right? So you have a bunch of lines, L1, L2, L3, L4, and you'll just binary search on this to figure out which one gives me the smallest x. When I say the smallest x, I mean more formally like each line has an intersection point for which it's useful. In this case, your L1 is useful till this point. Your L2 is useful from this point to this point. Your L3 is useful from this point to this point, and your L4 is useful from this point to infinity. So for a given X that you are queried, you'll just try to figure out in which range does this X lie? Does it lie in the range from minus infinity to this point, or from this point to this point, or from this point to this point, and so on? In which segment does it lie? And you'll binary search for that, and you'll get that in log. In this particular question, you don't need to binary search. You can be even faster than that in amortized sense, because you can slide over your lines. And the way it's implemented is you have this variable called pointer, keeps track of the best line. And when you're querying, you're getting this property that you're always querying with increasing x's, just because of the structure of this problem. And you say, ignore this condition for now. I'll explain it briefly afterwards. What you're trying to say here is the important thing is, for the current line, that is where my pointer is, what's my y coordinate that comes out for that line? So let's say my pointer is right now pointing to L2. So I say m of L2, that is the slope of line L2, times my x plus, which is bad notation, I guess. You want to say m2, which is basically the second line's slope, plus second line's constant, wherever this evaluates to, which is your y2, is it bigger than the next guy's y, which is m3's evaluation, which is y3. If y3 is smaller than y2, then I know I should move to the right, because I can get a smaller thing out. Right? In this example, geometrically, you would think about it this way. Let's say your x is here. This is your queried x, and right now your pointer is on L2. You'll figure out that for this x, L2 evaluates to somewhere here, which is say value 30. And you'll figure out your L3 evaluates to something smaller, which is say 11. Since 11 is smaller than 13, you'll be like, I'll move to the next line. So you'll be like pointer plus plus, because L2 is no longer useful because L3 has overtaken it already. So move to the next line. So that's what this implementation is doing. That keep on sliding to the right till the time the next line gives you a better y than your current line. And then when this stops happening, or when you reach the end of the stack, which is basically this condition, at that point you stop and you just return the y from the current line that you are sitting at. What's the piece of code here that I skipped originally? This is basically saying, if your pointer is already far to the right, say you inserted in your stack L1, L2, L3, L4, and your pointer, because of some queries, has already come to L4. Right? That is a possibility. And now when you're inserting L5, what happens is your L4 actually gets popped out. And your L3 also gets popped out. Say that's the case. So you have a case where you have L2 and then directly L5, because L3 and L4 both got popped out. In that case, your pointer is still at L4. I mean, not technically L4, it's more like index 4 in this case of the stack. And index 4 doesn't even exist. Index 4 is somewhere here. Like there is nothing at index 4 in the stack. All right. So in that sort of case, when your pointer is at a higher position in your stack than your stack size, which can happen because you could have popped out some things from the stack and made the stack smaller, you can always argue that your pointer can be just set back to the last element of the stack, because originally you thought that your pointer being on L4 means that for the last X you queried, L4 was the best line. Since you have removed L4 and L3, the future X's that you will query, which will be further to the right, they will never try to use L2, because L2 is strictly worse than L4, which is strictly worse than L5 for the X's that you are interested in. Not generically, but for the X's that you're interested in, you'll only be bothered about L5 from now on. So that's why you can just reset your variable to this. So this is kind of like an edge case of this implementation. Any doubts on this implementation? I mean, and obviously, like you could have thought about this query thing also from binary search perspective. I can probably share some implementation of that also, but like same idea as I explained earlier. So you could get the query in either amortized O1 or order login based on like, are you getting access in a specific way or not? If you're getting access in a specific way, then you can probably get away with O1. If not, then you'll probably be spending login. And in your inserts, you definitely need a constraint like increasing slopes, decreasing slopes, something of that sort. Otherwise, you're just inserting lines arbitrarily in the middle of your hull, which is kind of like not always to the right. So you can't use the stack approach. And that's where the dynamic CHT will come in. So if no more questions, I mean, if you guys have any questions, you can just put them in the chat. But if you don't have any questions, I have another poll question. When can you not use a stack for the CHT? Out of these three scenarios, in which scenarios do you think the stack will definitely not work? So we already discussed scenario 3, which is if the queries are not sorted, we can still use a stack approach. It's just that when we are querying, we'll actually binary search over that stack, right? So this is not the answer because the stack still works. What about between option A and B? Cool. Yeah, so option A is correct. That when the slopes are not in decreasing order, when you're getting slopes in like arbitrary order, in this case, I could have gotten slopes like, say I get L1 and I get L2. So right now they're in decreasing order, but say I get L3 in increasing order like this. In this case, my stack doesn't help me. Why? Because L1 has already been inserted, L2 has already been inserted. Technically, L3 is also part of the hull. Like right now, this was my stack. And the new thing I want to create is L3, L1, L2. Why? Because your hull now looks like actually this. So L3 is part of the hull, but it just comes to the left, which is not a particular pattern in itself, because you're not popping the stuff from the right. You're actually like inserting this L3 arbitrarily in the middle. Right. So if you don't have slopes in decreasing order, you break the property of the stack that you want. So that's the correct answer. The y-intercepts don't matter. The trigger conditions that we have, that when we pop from the stack and when we insert in the stack, those trigger conditions account for the y-intercepts. Okay. Before we go to dynamic CHT, I just want to give like some thoughts here that the static CHT can be more powerful than this. You can do other types of questions also using static CHTs. And static CHTs are preferred mainly because you could implement them yourself, like without even looking at the code book or whatever. They are feasible to implement. They're not that tricky to implement. And they're fast. I mean, dynamic CHTs are generally slower. So if your question, like the question that you encounter, can be done via static CHTs, that's the recommended way to do it. So two things, right? First is, what if you have the same question, but the slopes were in increasing order instead of decreasing? That is increasing slopes, but still we are maintaining a minimum convex hull, not a maximum convex hull. If you do increasing slopes and maximum convex hull, we'll just reverse the problem. We'll be like, yeah, then it would be like, this is the first line, this is the second line, this is the third line, which is basically the same problem, just mirrored across the x-axis, which is not interesting. But what if you have increasing slopes, but still doing min hull, right? So if you're doing increasing slopes and still min hull, geometrically, how it will look like is, you have, say, it's even hard to imagine this. You have, say, L1, and then you have slightly increasing slope, say L2, and then you have slightly increasing slope, say L3, and so on, right? Do we need a dynamic CHT or can we avoid it? Basically, my question is that, can you think of a variant of your current implementation, the static CHT idea? Somehow you could like tweak it so that you could support another kind of scenario where you do increasing slopes, but for the minimum convex hull itself. Move from right to left to modify. That is correct. So you could still, exactly like the way I drew this diagram, right? That because your slopes are always increasing, you'll be moving from right to left. So you could maintain a stack in the reverse direction if you wanted. And the pop conditions would be similar still. instead of a stack, you could have thought about it like a, I mean, you think about it like a stack only, just from right or left. So yeah, that's the correct answer. And yeah, so pretty good. The follow-up question: what if whenever we add a new line, either it has the highest slope amongst all the previous lines, or it has the smallest slope amongst all the previous lines? Let me give you an example. So forget the original DP question. I'm just phrasing this question, like these two questions, as like potentially other DP problems that you encounter where the slopes don't follow a simple property, but like have slightly more complex properties. So what I'm trying to say is, say your L1 looks like this and your L2 looks like this. Now your L3, when it comes in, it either needs to have the highest slope, that is, it will look something like this, or it needs to have the lowest slope, that will look something like maybe this. And maybe one of these two things happens. Maybe it actually comes like this, that is, it has the lowest slope. Now in a future insertion, your L4, when it's coming, it could come either direction. It could come either as the highest slope, maybe like this, or it could have come as the lowest slope, maybe like this, whatever. So every time you get a new line, either it has the highest slope compared to all the previous lines that we've inserted in our data structure, or it has the lowest slope within all the lines that have been inserted in the data structure. In this kind of a scenario also, so I'm still giving you some property over the slopes that are being inserted. It's just that this property is not that nice, because it's not like they're always increasing, they're always decreasing. It's more like within the active set that we have right now, the new thing that's being added in is either has the min slope or the max slope. In that kind of scenario, do you still need a dynamic CHT, or could you get away with a tweak? Yeah, so that's correct. You could use a deck here. Basically, a deck is a doubly-ended queue. People who are not familiar with it could look at like std C++ deck or whatever in the STL, and deck gives you push back and push front and pop back and pop front. These four functionalities are the main powerful functionalities that you can push stuff to the front, pop stuff from the front, which is kind of like partially queued like stuff, and then do it same on the back. So it's like a, I don't know how you call it, maybe a two-sided stack or something. Bigger, yeah, like yeah, you can push and pop stuff from either end. So in this case, when you're getting a L4, it could be you're inserting it here, or it could be you're inserting it here. Either way, you are allowed to insert it in a deck because you have those push functionalities. And wherever you are inserting, it's possible that because of the insertion of this L4, you actually have to discard some things. If maybe L4 is coming here, then you're actually supposed to discard L1. And if it's coming here, maybe you're supposed to discard L3. So you also want the functionality of pop back and pop front to be able to work this out. So even in a case like this, it is possible to do it via static CHT, like a variant of static CHT. Yeah, so that's all with the static CHT stuff. And now we'll move on to the dynamic stuff, which is very much more practical, because a lot of times when you look at a problem, especially in like a ICPC environment or like a more time stressed environment, you might not even try to figure out a pattern in the slopes or the x's. And if you have a code book ready where you have the dynamic CHT code, you'll just be like, I've got the idea that I have to insert lines and like minimize on something or maximize on something. Let's just do the dynamic implementation. Why even bother thinking about whether it's a static thing or not? Because the dynamic thing is power-wise strictly more powerful. Obviously, runtime-wise, it could be slower based on like how you get your log factors or how you implement your thing. But it's like just a relatively more brain-dead approach. You have to think less when you're implementing the dynamic one, if you have the code book ready. For IOI, I guess it's like you probably won't have a code book, so just implementing this thing is a pain. So that's why you probably want to spend time thinking whether I can actually use the static approach or not. Yeah. So the motivating problem is as follows. You're given n cities. I think I copied off this problem from, I don't remember, one of the blog posts about CHT. You're given n cities and you have to travel from city 1 to city n. In each city, you get, you can buy gas at cost CK at the kth city. So you have like different costs of gas at different cities. and initially your tank is empty, and you spend 1 liter for 1 kilometer, and the cities are located in increasing excess. So on a number line, if you think about it, this is your city 1, this is your city 2, so on, this is your city K, right? And each city has a different cost of gas at which you can buy gas from that city. And when you're entering the city, you have to pay the tax called toll K of that city. So maybe we'll denote it by TK. So T1, T2, T3, TK. Only if you stop at a city, you have to pay this toll. If you're crossing that city, you don't have to pay this toll. I'm just making the statements clear. So if you skip X3, that is, you don't stop there because you don't want to fill gas there. You could just skip X3 and directly go to X4 or like some other city, and you will avoid paying T3. Otherwise, if you stop there and you'll only stop at places just to pay the, like just to fill your gas up, you want to make the trip in the minimum possible cost. It is obvious that the solution can be calculated via DP. Okay, it's not that obvious, but like, yeah, you could do it. So I'll just give the recurrence out quickly because in a CHT session, our general idea is not to, like, a lot of times this is more like a skill of like DP, that how do you figure out it's a DP and how do you come up with the recurrence. Once you've come up with the recurrence in a CHT class, our emphasis is more on how do we optimize this recurrence, or like how do we run this recurrence fast in runtime so that we are able to get away with the problem and like not run into n square solutions, right? So in this case, our recurrence is as follows. So DPI denotes intuitively what is the minimum cost to reach city I. And when I say reach, I mean more like land on city I. So you're paying the toll on the ith city, plus you're saying there should have been some city before the city where I would have stopped. So say these are all your cities, 1, 2, I. You maybe stopped at some jth city here, and you would have filled up gas at this city for the distance from this city to the ith city. That is, you would have traveled from xj to xi. So this is the distance that you traveled. And for that distance, you would have filled up your tank here at the jth city, which would have costed you CJ per kilometer because you spend 1 liter per kilometer. So you multiplied with CJ to get the cost of the total amount you paid to travel this distance when you filled gas here at CJ at the jth city. And there must have been some cost to come till the jth city also from city 1, which is DPJ. And you could have tried different J's. That's the recurrence, right? Maybe instead of stopping at this jth city, you could have stopped at some city to the right, maybe some city to the left. But the idea is that from that city, you directly came to city I and you just skipped over the remaining cities in between. So what's the best way to do this? So that's why you have a min. In the examples that I have, I'm just like, I have the minimum examples, but you could have like max examples also here. It's the same idea. Like CHT works with max, just to give you guys the overview. So that's your recurrence. Now, do you guys, okay, let's not go through the next slide first. First, probably try to open up this expression, think about it more, and just try to come up with the slopes and the constants that you'll be inserting in your CHTs. What will your MJ and CJs look like? Let's just take 2 minutes here. Just think about this recurrence. Prefer not to go over the next slides because like, I think I give out the solution later, but like, or like, even if you know the solutions, try to work it out yourself, that how will the MJ and CJs look like? Because this is a useful exercise, because I think the most tricky part in CHT that people find generally is that how do they, like, once they see a relation, they generally see like multiplications happening. They don't see quadratic stuff. So they're like, probably a CHT can be applied here. But just coming up with those MJs and CJs is the important aspect. Because once you have that and you have a code book, you can code this stuff pretty fast. So, yeah. Okay, so Shreyas has one. He's saying MJ would be CJ. Okay, cost J. Yeah, my bad. Bad name, but yeah, cost J. And CJ will be DPJ minus XJ times cost J. Okay. I think that is correct. Yeah, that's correct. Yeah, I think that works. Yep, that's correct. So what you do is you first simplify this expression. When I say simplify, you just open up this multiplication, right? So you get cost J times Xi minus cost J times J. So you get these three terms, right? The terms, when I'm saying terms, I mean this thing is one term, this thing is one term, this thing is one term. Generally, what you have to look at is what's your, in your equation, y equal mjx plus c. It's more like yj equals mj times xi plus cj. That's what your equation actually looks like. That you're calculating the y for a given j, that is yj. You're picking a slope based on j alone. You're picking a constant based on j alone. But the x that you're feeding in is your live x, something which is like the thing that you're feeding in. In this case, what's your I? Your I is here, right? So this thing being multiplied is actually the slope of your equation, which is cost j, which Shreyas said. And your C is all the remaining thing. Fortunately, in your C, you don't see any I occurrence. So when I say you don't see any I occurrence, I mean, when you calculated for, say, j equal 5, your dp values or whatever, at that point itself, you could have inserted the mj, which is cost j. You knew that at that point itself, right? You knew what's the cost of gas at the 5th station. And you knew what's the cost of gas at that station times mj, sorry, times xj, which is the location of that city. This is in the minus sign. I should clear this up a bit. This is the minus sign, right? Plus, you calculated the dpj also. That is what's the best way to come to the city. So this entire portion becomes your cj because it only has j's. It doesn't have I in it. That's why you can do this. So blah, 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 simplifies to this, and then your m becomes this, the cost becomes this. Another thing to notice here, quickly, do you have any pattern in m? Will your slopes be always increasing or decreasing as you're inserting new slopes in? No, right? Because you could have like the second line slope in the 5th lines, like, sorry, second city's cost and third city's cost, there is no pattern. Like the question doesn't specify anything that the cost of the gas will always be increasing up as we go larger city to like higher numbered cities or whatever. There's no such pattern. So you don't have any patterns in J, like in the slope. Also in your query, do you have any pattern? You're querying on xi. So actually you do have a pattern in your queries because you're always querying on a increasing x. So maybe we could do a sliding window approach. Like we can think about it later, but like maybe that's possible. But definitely you can't do static CHT because your slopes has no pattern. It's not like your slope will always be increasing or decreasing, or even the other variant that we discussed, which is that it will either be always the highest slope or always the smallest slope. Even that's not the case. It could be like, oh, you have like L1, L2, L3, and maybe the new thing just comes in like L2 dash, which is like high, like larger than L1, but smaller than L3 or whatever. So you don't get any patterns. So now you need a dynamic CHT. That is, given insertion of lines where you don't have any pattern in slope, how do you maintain your CHT? So that's the question now, right? If you could do that fast and support the query method also, you're done with this question. You could just figure out this portion of your recurrence fast, add toli, calculate DPI. And then once you've calculated DPI, you'll be like, I'll insert the new line in with cost I as my slope, cost I times xi plus dpi as my constant, whatever the Snyder's line is constant, whatever the new line can also be inserted. So how do we make a dynamic CHT? That's the question. Okay, first I'll go through two ideas where you just leverage the static CHT that we were able to build and just exploit them. I'm not recommending them as like your go-to solutions or anything of that sort, but it's useful to know how you modify static data structures to dynamic data structures. This is not a super generic technique, but it can be used at other places also, maybe like for centroid decomp or like other data structures that you think of, like DSU. I know that this thing for sure works for DSU. This thing I know works for like some other places. So it's useful to know about these techniques in general. And obviously, like for CHT also, I know people who have used them in the past. This becomes especially relevant if you don't have this like CHT, whatever code in your code book, or you are preparing for the high school Olympiad where coding a D like dynamic CHT from scratch is a non-trivial task. So you might just resort to coding a slightly slower version of dynamic CHT, which is basically static CHT plus, like static CHT plus like powered up based on like either of these two techniques. So what's the first technique? It's the square rooting method. What you do is you maintain a bunch of CHTs. And when I say CHT, I mean like a stack or whatever, like that's one instance of a CHT. And when a new line gets added, so say you have like L1, L2 up to say Ln already inserted. And like this is like a root n sized stack, this is like a root n sized CHT, and so on. And now you get a new line called Ln plus 1. If either you start a new buffer, right? Or you already have a buffer which is like smaller than root n size and you add this thing to it. Basically, you can maintain like root n sized buffers, contiguous, and the new thing that comes in either gets added to a new buffer or the last buffer that you have, you expand on it, right? And once the buffer size hits square root n, you bake the buffer. When I say bake the buffer, what you do is, so once this buffer is of size n, so till the time the buffer is not of size n, till the time this buffer is not of size root n, which is like, say, it's only consisting of Ln plus 1, Ln plus 2, and whatever, like say 10 lines. You just keep all those 10 lines in a vector or a set or whatever. You don't actually create a CHT out of it yet. Now, once it hits the root n constraint, say your root n is actually 12. So you added a new line and it became 11, and then you added a new line and it became 12. So you're like, okay, now it has hit my threshold. I'll just bake this thing up. When I say bake this thing up, you'll just take all these lines, sort them based on their slopes. Now you can sort them because they're already in, like you already know that these lines have been inserted. Like they are part of your geometrical figure, right? Maybe some of them are useless, but you are allowed to use them. Maybe just some of them are bad lines, like they give you like very high Ys or whatever. But you sort all of them by their slope. And once you've sorted all of them by their slope, you can just run a static CHT and insert them from left to right. So once your threshold is reached, you bake them. And when I say bake them, you construct a static CHT out of all of them and calculating the CHT on it. And whenever you're querying, what you'll do is you'll have a bunch of baked buffers. This one is baked, this one is baked, and so on. And the last buffer is technically not baked. It's just a bunch of lines. So when I'm querying for a given x, say x equal 30. Oh, my bad. So when I'm querying for say x equal 30, I'll be like, I'll query for this x in this buffer, in this CHT. I can do that in like maybe log n, maybe O1, depending on whether I have to binary search or whether I have to slide over it. And then I'll do that same here, do that same here. And in the last buffer, which is not yet baked, I'll just evaluate that x equal 30 for each line individually. So I'll just plug in m times 30 plus c for each line. So like each line will have a different slope and constant. I'll just plug them in, keep on plugging them in and calculate all the y's. And out of all the candidate y's I get, I'll get a candidate y from here, I'll get a candidate y from here, and each one from here. At most, I'll have at most 2 root n candidate y's, and I'll just take the minimum over all of them. So that's the square rooting method. So notice your query time is square root n times how much time it takes to query on one CHT, which could either be O1 or it could be log n, depending on like whether you have like special benefits with your x's being sorted or not. And your insertion time is, if you're doing just an insert where you're just adding a line here, it's cheap, right? Because you're not even baking the buffer. So it's O1 in those cases. But whenever you're baking a buffer, you are just sorting this entire thing and yeah, basically spending the cost of sorting it, which is like square root n times log of square root n. But you're only spending this cost in an amortized way. That is, for every root n lines you insert, you bake after inserting all those lines in. So you spend this log square root n, whatever this cost, after inserting root n lines. So for a single line, you're actually just spending log n time, like around log n, whatever, log root n technically, which is like half log n, but like, yeah. So your inserts are pretty powerful, but your queries are slow. You could play with your root n. I mean, you can just map this out and like figure out what your root n should be. Maybe it should not be root n, maybe it should be something slightly higher than root n, but it's a blockish approach. And that's one way to do this kind of question. If you just want to leverage static CHTs. What's the other way? The other way is amortized power of 2. I don't know what's a better way to call this thing. So I just named it amortized power of 2. It's a trick mentioned in this blog post. It's a very useful blog post if you want to look at it, not even from a dynamic CHT point of view, but like for other techniques also. It's pretty old blog, but like it has a lot of useful techniques that a guy named Adam Anton CF wrote about. But one of those techniques is this one, which is what? This basically means, I mean, you can read through this, but I'll just give you the high level idea. Say you have 10 lines inserted in your CHT right now, right? So your number of lines inserted is 10. Pencil is slightly weird. Maybe I have to change my number. But yeah, say you have 10 lines inserted. Now your 10 in binary representation is 2 plus 8. Right? So you'll have a CHT of size 2 and a CHT of size 8. You'll have two CHTs based on the binary representation of 10. Say your n was actually 12. Then in the binary representation, it looks like 1100, 8421. That is, you have a CHT of size 8 and a CHT of size 4. Or whatever, right? So you will have at most log n CHTs, because even if your n is big in binary representation, when you look at the binary representation, wherever it's a 1, you'll have a CHT of that size. Say maybe it's 32. This is 16, but it's off. This is 8. This is on. This is 4. This is off. This is 2. This is 1. So the number itself is 32 plus 8, which is 40 plus 2 plus 1, 43. So for 43, you have like 4 CHTs. One of size 32, another of size 8, another of size 2, another of size 1. And now when you get a new line, say, so let's just take this example for now, that you have a CHT of size 43 and its binary looks like this. So you have a CHT of size 32, you have CHT of size 8, you have CHT of size 2, you have CHT of size 1. And now when you get a new line from 43, you are adding a new line in. What you'll do is you'll think about it in terms of like, how does the binary number increment? So in my binary increment, I'll add this new line to my one sized CHT, this CHT. And I'll reconstruct the entire CHT. So I'll sort all the slopes like within these two lines and just reconstruct the entire thing. So now I'll have, so what did I originally have? I had a 32 size CHT, an 8 size CHT, a 2 size CHT, and a 1 size CHT. And I added a new element 1. Because there was a 1 size CHT already, I merged it in this one and recalculated that entire CHT. So I spent some time, but I came up with a 2 size CHT. Now, since there are two size CHT, I'll merge them again. And I'll like sort all the slopes within these 4 lines and come up with a 4 size CHT. And now, because there are no 4 size CHTs apart from this, I'm just done. So this is, now you have 44 lines. Now maybe another line comes in. In that case, you'll just insert a new CHT of size 1. So n equal 45. And so on. And maybe another line comes in, and at that point, you'll create a new CHT of size 1, but then you'll realize that, oh, there are 2 CHTs of size 1. So I'll just merge them together, sort their slopes or whatever, reconstruct the entire thing, and come up with a 2 size CHT. Now, this might look slightly slow in the start. Like intuitively, you'll think that, damn, you're just adding a new line, reconstructing the entire thing again and again, and you're like wasting a lot of time. Just go through this or whatever. If you think about it carefully, you'll realize that this complexity is being amortized. very smartly. You're not spending a lot of time actually reconstructing stuff. And the heading of this trick, which is basically this from static set to expandable set via login, it kind of gives you the clue that you're spending login extra time because of these reconstructions that you're doing. So if your original thing could be done in time, I think they represent the time as a function of n, like fn, then you could do the new thing, like from static to dynamic, you could go in fn login. In our case, constructing a static CHT takes us time n log n. If you have n lines given and they are like just random slopes and you have to construct a CHT out of them, you'll sort the slopes and then you'll just put them left to right in your stack approach. So it will take you n log n time. Because you're doing this technique of like merging sets and reconstructing stuff, you'll actually end up spending n log square n, which is not particularly bad. Getting like saying that you got the power of like dynamic CHT from a static CHT. So are these two variants clear? Like just the high level ideas of like how you could leverage the static CHT to get a dynamic CHT. And like, I know the second trick for sure works in DSU also. So sometimes there are use cases where you want to do it for DSU or like suffix arrays or like other data structures also. I couldn't understand the query in the second time. Oh yeah, I did not explain the query. Yeah, that's valid point. So say you have n equal 44 done or whatever, and you have like 4 CHTs. One is 32 size, one is 8 size, one is 4 size, one is 2 size. Now, when you're querying, you know, I'll query all 4 of them. So for a given X, I'll query this 2 length CHT also. And it'll take me just log in time because there are like, whatever, like if there are 32 elements in a CHT, nobody cares that there are 32 elements in the CHT. You could just binary search in that CHT to figure out for this X, what's the best value that this CHT gives me. And similarly, you'll query for that X in the other CHT and so on. So you'll get this, like your query interface is basically log number of lines you have in that CHT. And in this case, in each CHT, you have at most n lines. So for each CHT, you'll spend at most log n time to query that CHT. And you have at most log n CHTs. Reason you have at most log n CHTs is because whatever your current n is, you have to think about that n in base 2 and only the locations where that bit is on, those sized CHTs you have constructed right now. So even if your n is big, the number of CHTs you'll have is just log n, because when you do binary representation of n, you'll have at most log n active, like 1 bits. So log n CHTs, and per CHT you are spending at most log n. So per query you're spending at most log square n. So your queries are fast. I mean, I think that's the benefit of this guy versus the older guy. In the older guy, I could see that these queries are relatively slow. It's like a root and a log and or whatever. Any doubts regarding these two techniques? Cool. Then I think we move forward. Yeah. So the other typical way to do dynamic CHT is actually to use a STD multiset. The recommended way to do dynamic CHTs, the code of this I've copied off from some CF blog post or whatever you can find. Like this is the implementation link, and in the further reading section which I have down here, I actually state all the resources that I used for this presentation. Like at least these are the useful resources that I found on like Lee-Chow and static CHT, dynamic CHT, all that stuff. And there also someone covers this implementation. Just a header for this implementation. I don't understand this implementation fully. I get the high level idea that you're inheriting from a multiset to get the powers of a multiset. But the thing is like super tricky. They have a struct line and they have 2 overloaded operators for the less sign. One is with compared to the other lines, which is useful because their K is more like the slope of the line. If you notice here, no, your K is not the slope. Your M is the slope. And your P is the point of intersection. I can explain this later slightly. Actually, my bad. Your K is the slope. For some reason, these guys have like super bad notation. Your M is the C that we used to have, and your K is the slope. And they have like two overloaded operators. The line one is simple because you're just looking at the slopes, and based on like whichever thing has the smaller slope goes to the left in your multi-set. Multi-set is basically like a set, but only that you could have like same things again and again. And the larger thing goes on the right, the higher slope goes on the right. Notice one more thing, it's mutable set. Like these variables are mutable in C++. The reason you want to have these mutable is when you're inserting something in a set and you're changing the value of the element itself, you want the set to rebalance, or like your red, black tree, or whatever your underlying implementation, if you want it to rebalance. And the way you kind of enforce that is that you make those variables mutable. So you say, I can change those variables. And when I'm changing those variables, I actually want my rebalancing to kick off by the STD, red, black, whatever. I think they do AVL trees behind the scene for STD set, multi-set. So you want those rebalancings to happen because you could be changing attributes of the lines. Yeah. And the second part is you have an overloaded operator with respect to another value, like an integer or a double you want to think about, which is x, and that you do via the point of intersection. This operator, the second overload operator, is slightly unintuitive, but the reason why they have defined it is because in the query, they want to use the lower bound method of the STD set. In STD set, you have a lower bound method. You can just call like s dot lower bound with a given x, and that lower bound method will actually like give you the smallest value that's just larger. In this case, the comparator that's being used for this implementation is this guy. And whatever that gives you, you just pick that line and just evaluate that line. So that's how the query works. The add is way more complicated. I mean, the code looks very small, but it's like they do a lot of tricks here. So that's why I'm saying that even I don't understand it fully, but it's a useful piece of code, like to keep in your code book. The high level idea I can explain, which is basically, I copied off this from WCIPG, that website, which has like a very nice blog post about CHT in general. It doesn't cover Lee-Chow, but it's a useful blog post, like if you're first time getting familiarized with CHT. And what they explained basically is that you can support arbitrary insertions in amortized logarithm time. To do this, you store the lines in an ordered dynamic set, such as STD set or a multi-set. Each line possesses the attributes of slope and y-intercept, what we discussed earlier. The former being the key, that is the slope is the key. So you're sorting the things by slope. Ignore this left field for now, but like, yeah, there is some left field. Okay, what this left field means is basically, I think, yeah, I should just explain what the left field means. The left field here is analogous to the P field here. What it means is that if you have a line, say this guy, I don't know why my tablet, like maybe it's ran out of battery or something, depends. Say you have this line L1 and you have this line L2, then for L2, this is your P, that is its point of intersection with the previous guy. And for L3, this is your, say this is your L3, then for L3, this is your P. So that's what the P means in this case. When you're inserting a new line, you insert it in its correct position in the set, and then you have to decide which lines have to remove. So that's the tricky part, right? In the dynamic set. Then in the static one, you were always inserting things to the right, and you would just like have some sort of condition based on the stack that what will I pop from the rightmost position. In this case, it's slightly different in the sense, if the line is to be added is L3, then the line to the left is L2 and the line to the left of that is L1. So let's say L3 is being added here, then you just like based on the slopes, you say that this is L1, this is L2, you just label them intuitively in your mind. And then again, you check whether L1, L3's intersection is to the left of L1, L2's intersection. If so, you remove L2 and you keep on doing that. So when you're inserting something in the middle of your CHT, you're like, this line is being inserted. What's the previous line to this line, slope-wise? And what's the second previous line? And label the second previous line as L1, the previous line as L2, the new line being added as L3, and then decide based on your typical condition that we were doing in stack, whether that L2 line that was already there is now useful any longer or not. If it's not useful, throw it away. And when you throw it away, your L1 becomes your L2, and your L0, which is basically the line also more to the left of L1, that is, it has a smaller slope than L1, that becomes your L1. And you again think about the L2 line as whether I can discard it or not, and you keep on doing that. And similarly, when you're inserting a line L3, it potentially also has a right line to it, L4, already in the stack or like your CHT, and a line L5 also in your stack. So that's what it explains. Then similarly, if line L4 and L5 are on the right, then L4 can be removed if L3 L5's intersection happens to the left of L3 L4 intersection. So basically, the line immediately before you and the line immediately after you are the ones that are in danger because of you being inserted. They could potentially get removed. And if they're removed, then the new lines that are immediately to the left of you or to the right of you are in danger. And you keep on removing those lines until no more lines can be discarded. And once no more lines can be discarded, we figure out our left value. That is, say L2 is being added, but because L2 is, say L3 is being added, but because L3 is being added, it actually kicked out L2. Like, let's say this was L2 and this was L3. So because L3 was being added, L2 got kicked out, and then your point of intersection for L3 with respect to L1 will be here. So that's the high level idea. Then whenever you're inserting a thing, you're removing some things from its immediate left, some things from its immediate right, then figuring out its point of intersection and actually inserting it into the set. So in your add, you can look at it. They first insert it into the set here. Once they've inserted into the set, they remove stuff from the right because they're doing this like thing and like they keep on removing stuff from the right. And then they also remove stuff from the left. Which is basically this portion where they're removing stuff from the left also. But I can't explain this portion in detail, to be honest, because like they do a lot of stuff here. They do like pre-increments, post-increments, a lot of comparisons, a lot of like C++ hacks. I personally don't like this code that much, but at least from the reviews that I read on CF, this is a super fast implementation of dynamic CHT. And it's super concise. So I think like from a ICPC code book point of view, it's very relevant because you have to write a lot of like very less code to get the implementation out. So that's the dynamic CHT's idea. But like I think this particular portion in that WCA PG web page is the most useful portion because it gives you the explanation of what you're trying to do actually when you're maintaining a dynamic CHT. There are simpler implementations online. You can look at them, and like I've coded some before, which are much more reasonable. Like you can actually argue about them much more easily. It's just that they're slightly slower than this and not as concise as this. So I would recommend that if you want to put something in your code book, just put this one. Maybe a follow-up question for everyone. Right now, till this point, we always discussed a minimum CHT. That is, you had your lines like this. Sorry. Okay, you can actually avoid the scribble by doing this. So you always had lines like this. And because you had lines like this, you were always doing minimum CHT. What if we were to do maximum CHT? Same question. Like the DP recurrence is now max instead of min. How would you tweak your implementations in the easiest way possible to get max out instead of min? Think about the easiest way that you can do it. Obviously, you could do like, I'll flip all the conditions and I'll start using max variable, like start using maxes everywhere instead of mins or whatever. But if you want to do like, yeah, just think about it. What's the easiest way to leverage the min CHT, static maybe or dynamic, maybe whatever implementation to get the maximum out, like to get max values out, where your question has changed to basically saying you're inserting a bunch of lines, and for a given X, you want to find out which line gives you the maximum Y. Any ideas? So like in this, it's like a trivial trick once you get this. Yeah, so Hari is correct. Yeah, that's all. So originally you had, this is such a big font. Originally you had line L1 equals M1 C1 and L2 equals M2 C2 and so on. And now instead of these, you'll just store the negatives. So you'll have like L1 dash equals negative M1 negative C1 and so on. For all the lines, you'll store the negative slopes and negative C's. You'll just multiply with the -1. And when you're querying for your X, you'll also negate that X. So if you're querying for X equal 10, you'll instead of querying for X equal 10, you'll query for X equal -10. And what you'll get is in the negative world, you'll get the minimum. And once whatever value you get as the minimum, just multiply it with -1 again. And that's your value in the maximum world. So pretty straightforward. So you can like, if you have one implementation, you don't even have to like change the implementation. You can just, whatever slopes and C's you're putting in, just multiply with them with -1 and pass it to your interface. So that's dynamic CHT. Now, although I did explain all the nitty-gritty details of dynamic CHTs, how you can do it via static CHTs and how you could actually do the STD multiset version, I won't recommend to actually code any of these. The reason being, this is still slightly slow, slightly less powerful. There is another thing called Lee-Chow. It's not strictly Convex Hull Trick, but it's like always discussed in tandem with Convex Hull Trick. And this is generally more powerful than CHT. I'll just go through that slide here, the things that I could find about it. So Lee-Chow is more powerful than CHT for the following reasons. Easier to make persistent. If you know about persistent data structures, you'll realize once I explain the Lee-Chow idea that it's much more easier to make persistent. Making the CHT persistent is like super painful, especially a dynamic one. A static one you can still make persistent. A dynamic one is just like, you'll have to kind of unravel the balance binary search tree implementation of STD set or whatever, and like do it yourself. So it's not trivial at all. Easier to code. I can show you the Lee-Chow code. It's like super straightforward. Everyone can understand it and whatever. Faster runtimes. It generally, if you look at Codeforce's blogs, or like, yeah, I can maybe share some of my like submission times or whatever. People have a consensus that Lee-Chow is faster because it's like less of like STD set, STD multiset stuff, and like STD set multiset has like high constant factors because they're rebalancing stuff a lot of time. And it allows you to insert things which are not strictly lines. Maybe it could be like a segment of a line. The problem that you are particularly tackling does not actually give you lines, like indefinite lines, but a line is only defined from like a certain point to a certain point, and it's not defined at the other point. So it's a line segment actually that you're inserting. If you have those kind of line segments, or you have other functions that maintain the property that they only intersect once. Lines have this nice property that if you have two lines, those two lines will either not intersect because they're parallel, or they'll intersect at most once. You can't have two lines which intersect twice, right? That like the second thing is not line in this case. So you get this property for lines for free. But if you have some other kind of function which also gives you this property, and you want to maintain a min hull or a max hull, you can use Lee-Chow. So it's pretty powerful in that sense that I know there have been questions where you've been given quadratic equations, but with the same, whatever you call it, curvature. Like this is the curvature of one of them. I don't remember what this thing is called. It's probably 4AC or something, but whatever it is. And a bunch of quadratics, but all with the same curve. And maybe this one is slightly lower or whatever, but you get like, you could argue in that kind of question that all these quadratics intersect with one another at most once. So if you pick this quadratic and try to calculate their intersection point, it only happens once. Like that was a property that you could have formulated in that question. You were given that property for free. And because you were given that, you could actually apply Lee-Chow to get a min hull for that quadratic, which is like super fascinating. So you could get something like this. And like Lee-Chow actually gives you that you can query over this min hull fast. And I think a good video about this Lee-Chow, like this quadratic idea at least, is, I'm not sure which one is the YouTube video. I think this one It's Algorithms Live by some YouTuber. I don't remember him, but like there is this nice YouTube channel that used to be active like 3 years back or something. And they posted like 20 videos or something. And one of their videos is based on this quadratic idea. I haven't gone over the video fully, but it's a good idea to know of that. If you have like quadratic scenario or something, or like till the time you can argue that your function satisfies this property, you can argue that Lee-Chow can work. So yeah, probably I've convinced you that Lee-Chow is powerful, right? So what is Lee-Chow? Lee-Chow is kind of like a segment tree in some way. And you're given a set of functions such that no two intersect, like two at most once. This is the property that you want. I think I took this from CP algorithms. So it's a widely available resource that I'm sharing right now. And you're making a segment tree on the range that you'll be querying. So your X has to be reasonably small. Like maybe you're querying from 1 to 10 to the power 5 each time. Or maybe you're querying from 1 to 10 to the power 9. If you're querying till 10 to the power 9, then maybe you can't create all the nodes of your Lee-Chow live. You'll probably have to do some pointer stuff to like lazily create your Lee-Chow as and when necessary. And what you do is whenever you're querying a specific X, you'll just dig deep into your segment tree for that leaf of that X. And you'll get this guarantee that if we go from root to leaf, we'll definitely encounter one of the lines. Just think of this function as line always, because in our use case, when we are using Lee-Chow for CHT, our functions are just lines, right? So you'll definitely encounter one of the lines that will give you the minimum value. So each node of your segment tree has a line associated on it. And for a given X, when you're going down your segment tree, you'll definitely find one line which has the value that you want. So say your segment tree looks like this. And so on, right? And this is say X equal 3. And there will be say line L1 here, L2 here, L3 here, L4 here, L5 here. The guarantee that you are getting is if you're querying for X equal 3, when you go from root to this leaf, within these lines, your optimal lies. So if you calculate your Y for this line with X equal 3, 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 and you take the minimum over all of them, you'll definitely get your answer. Other lines which are like L3 or maybe L6 or something like that, these lines are not useful for you if you're querying for X equal 3. This is the property that Lee-Chow gives you. So that's why your query is just straightforward, and you just go from root to that leaf. And for each node that you're on, you query that line and take the minimum over all of them. How do we construct this Lee-Chow? How do you get this property out? For each segment that is L2R, it's a half segment because R is not included. Ignore that detail. You have a function on it. I again said, think of function always as a line in our case, because we're just working with line in CHT. F old, and you're inserting a new thing. So say in this particular case, I'm inserting a new line from X equal so let's call L1 as F old, right? And I'm inserting a new line over the entire range. Why I say over the entire range? Because it's not a line segment, it's an entire line. So that line could potentially impact multiple places in the, like not multiple places, but like it impacts the entire X range, right? So your new line is called F new. That's the variable convention that these guys are checking within this blog post. And you say that if F old is already in and we're adding a new line F new, so this diagram is useful. Your F old looks like this. This is your F old. This looks like this. Say this is the line. And this is your 1, this is your N, this is your mid. Right? Notice at mid, and the new line being inserted is this one, which is like opposite slope, right? Notice at mid, your old has a higher value than your mid. Sorry, your old has a higher value than your new. So at the intersection point, you'll realize that your old has a higher value than your new. And you'll decide that I'll not replace the old with the new. The idea of Lee-Chow is that the function that will remain on that node, or the line that will remain on that node, has to be the one that is the best for that mid. has to be the one that is best for that mid. In this implementation, I think they're doing maxes everywhere. So it's actually a max hull. So yeah, I mean, the blog post that I copied of these details from, it's actually a max hull. It's not a min hull. Intuitively, it's the same. So in this case, the constraint that they're trying to maintain is your function f hold is kept there, and we had blah. M is mid. I don't think they've mentioned it anywhere explicitly, but I can say this for sure, that the line that remains on that node has to be the one that wins on the midpoint. Wins meaning in this case it's a max hull, so it has to be the higher one at that midpoint. So if your old is this and your new is this, since the new is losing at the midpoint, you'll be like, I won't replace my f old with the f new at this node, but maybe at some child node. And how do you decide which child do I have to go to? Do I have to go to the left child or to the right child? That's where the trick lies. You'll figure out that your new beats your old on the left side, which is here, right? This is the place where your new is actually beating your old. On the right hand side, it's strictly losing always. So you don't really have to go on the right hand side in your segmenter. You only have to go to the left. And that's what you like. That's the important thing in this entire implementation idea, that you can always figure out that you only have like one direction where the new thing is actually useful and the other direction where the new thing is not useful at all. So just go to that direction where the new thing is useful. And maybe in that direction, the new thing starts beating the thing that's already present. If that is the case, swap that old thing with the new thing. When I say swap, I mean the old thing could still percolate down further in one of the directions, but the new thing is now the winner at this range because it wins at the mid. So, I mean, they probably explain this here. We can compare the values of the function and points at an end. If the dominating function changed, then we are going in this direction. This is basically just explaining the part where you decide how do you know where is new potentially winning? Is it winning in the left-hand side or the right-hand side? This is based on these conditions. And we recursively keep on going to the segments. And the correctness argument here comes from the fact that on a given node, you always store that line which wins at the midpoint of that node. So I'll probably go through some code of this and like maybe you guys will understand this better. So you have a struct line. It has this M, the B, again, the B is actually the C. And you have an operator, which is like for a given X, if you want to evaluate this line, you'll just return an X plus B. You create your segmenting, it's like a 4 times n sized array. In query, it's very straightforward. If you are given a left range, a right range, a querying X that you're interested in, and a O, which is like the node ID in your segment tree. If you're at a leaf, you just, whatever line you have at that leaf, just evaluate that line for the given X. So that's what this code does. It evaluates that line for that given X. And if you're not at a leaf, you calculate your mid. You calculate your left child segment tree's node value, right child value, 2i plus 1, 2i plus 2, typical segment tree stuff. If your X is to the left of the mid, then you just query on the left side. Otherwise, you query on the right side. And what are you querying? You're returning the max of the current candidate versus what you find from the left side, or the max of the current candidate versus what you find from the right side. So you're like maxing over two things: the current candidate, which is this thing, and the left side's recursive query or the right side's recursive query, and taking the max over of the entire thing. So query, I think, is straightforward, right? That each segment, like each node of the segment tree has a line associated with it, which is denoted by A of O. And you can evaluate that X over there, which is called by A of O of X. And you just be like, I'll dig through my segment tree to find that particular leaf and take the max over all the X's, like all the line evaluations within that path. So that's query. The time complexity of query is log C, where C is basically your range from 1 to n. So if you're querying over like 1 to 10 to the power 5, then it's small. If you're querying from 1 to 10 to the power 9, it's potentially big. You could do coordinate compression, all those sort of things in Lee-Chow also, just like you're doing typical segmentaries. Will be slightly convoluted, but you can. How does your insert looks? Now, insert is like slightly tricky for Lee-Chow compared to like typical segment trees, I'd say. If you're on the leaf, It's a simple question of whether the new thing that you're getting, the new thing is called seg here. So if you're on a leaf, if the new thing has a better evaluation than your old thing, then you replace your old thing because it's a max hull. So if you're at the leaf, you can't go anywhere below, right? And you're like, whatever I had stored here, that's useless for this X. And actually the new thing that I'm getting is actually better here. I'll just throw away the old thing. This is the only place where you throw away the old thing. Otherwise, you calculate the mid, the left child, the right child, and you're like, ignore this line for now. This is like a slightly tricky line, I'd say. This line is slightly tricky. Ignore this for now. You just think about this for now. So what you're doing is you're saying, evaluate the old line at mid versus the new line at mid. And if the new line is better, then swap the old line with the new line. So that is now the old line is actually the better line. The new line is actually the slightly worse line, and recurse for the slightly worse line to the left side of the segment tree. And if the old line is actually wins, then you don't swap because the old line remains here as is, and you recurse on the right side with the new line. Now, how could you say always that if the old line is worse than the new line, then we'll recurse on the left side? In this particular example, visually, you can argue that yes, it makes sense. That your old line is here, your new line is here. So your old line is higher than your new line, and you have to recurse to the left. In this particular example, it makes sense. But would it make sense always? Can you blindly say that I have to recurse to the left always? No, you can't. Why? Think about it this way. Say this was the no, my bad. I have to create some other example here. I think it looks like this. Say your old line was like this, and your new line was like this, and your mid was here. So your old line comes like say y equal 10, your new line comes at say y equal 8. This is your mid, right? So notice if this is your mid, your old line is winning on mid. So will you recurse to the left? That's wrong if you recurse to the left. Why? Because when you're recursing to the left, you're basically saying that on the left side, like the old line is winning at mid. So I don't care about the current node. My current node has the correct value, which is the old line. I have to figure out where is the new line's potential to win. But we see here clearly that the new line is strictly smaller than the old line to the left side. But on the right-hand side, it actually starts winning after a certain point. So you actually had to recurse to the right, not to the left. But in this implementation, you see that we always recurse to the left, like as a dumb thing, that whenever the old line is beaten by the new line, you always recurse to the left. The reason you can do this here is because of this line that we highlighted. That's the, like, I just wanted to give you the motivation of why this line is there. What this line is basically saying is that if the old line has a higher slope than the new line, just swap them. So because you swap them here, you can, after this line, assume that your old line's slope will always be less than new line's slope. So you could probably say it in a more concise way, like f old m is less than f new m. Old line slope is always less than new line slope. So you'll never encounter this kind of scenario because your old line slope here is less than your new line slope. So you would actually swap them beforehand only because this has a higher slope than this. So you won't encounter this kind of scenario. You'll swap this scenario to look like this kind of scenario. Or basically just think about like this is now old and this is now new, and then it starts working correctly. So everyone gets the idea of like, so I mean, this one particular line is like slightly tricky if you read this code for the first time, I would say, or like a code like this. And like you do a bunch of swaps, but I hope it's clear why you're doing those swaps and what's the invariant you're trying to maintain. You're trying to maintain this invariant that the line that's sitting on that segmentary node will be the one that wins on the mid. And you only have to go in one direction to argue for the new line that's being inserted, because that new line could only be winning potential, like in one of the regions, either on the left hand side or on the right hand side. And maybe the new line comes in and actually wins at the mid itself. Then what you're doing is, if the new line comes in and wins at the mid itself, you're swapping the new line with the old line, basically saying the new line is now the winner at this node. So it sits here, it stays here. And the old line recursively now gets treated as the new line, because maybe it's still winning in the right hand side region, or maybe on the left hand side region. And that you've figured out based on the swap condition. So is the Lee-Chow idea clear to everyone? That what's the invariant you're trying to maintain, and intuitively, why does that invariant give you this guarantee that when you're going to a leaf, just check all the lines in the path, and one of those lines definitely gives you your answer. The reason why one of these lines definitely give you your answer is because these lines are the best at their mids. Any questions? Yes, Hari, you're probably correct. Yeah, you don't actually need CHT with sets. I just explained it because it's useful to know that stuff can be done. But I agree with you that Lee-Chow generally works in most of the cases. I think the only place where I could argue that sets implementation for CHT makes sense is when you have high X's. If you have X's which are querying in the range of like 10 to the power 9, 10 to the power 12, or something of that sort, like large enough, like more than say 10 to the power 6 or 10 to the power 7. In that case, you can't actually maintain a Lee-Chow like this with this entire range here, right? Because your C will now be too large, which will be like 10 to the power 7, so you'll waste a lot of memory. So then you'll have to either do a pointer implementation for your Lee-Chow, which is also possible, but like slightly more convoluted code, or you'll just resort to using dynamic CHT. The thing is, Lee-Chow works on a range of X. So if your range of X is quite large, you're spending like all your log complexities don't come in terms of number of lines. It comes in the number of like your size of your range. I think another interesting thing that I've seen people raise in the past is Lee-Chow does not work on like if your X is actually like 3.7, 3.8, 4.2, if your X is a double, it's not an integer. If those kind of scenarios also, you don't like either you discretize your Lee-Chow on a more granular level, say not on integers, but on like decimal points up to 2 values like 0.00, 0.01, 0.02, whatever. Either that sort of thing, like you just discretize it on a smaller scale than 1 unit, or you use CHT. So, I mean, the inherent downside of Lee-Chow is that it works on ranges, not on lines, like not as a collection of lines, but as a range of things. So that's the one obvious downside. Otherwise, I do agree that in general, it's easier and it's more powerful. So that's all. And I guess I'll probably stop here and like maybe just either we can have a session later, or I can just share these slides and like have a discussion on the class channel or some other place. Basically, these were like the 2-3 other things that you guys might be interested in. One is Lee-Chow with deletes. In a dynamic CHT, it's not at all obvious how you can do deletes. When I say deletes, I mean you have a bunch of lines inserted in your CHT already. Now you decide I have to delete one of the lines. And when you say I have to, like, think about it this way. When you inserted a line, you potentially threw away some line because this new line that came in actually beats a lot of previous lines, right? Now, when you're deleting this line, you have to kind of ensure that I undo that throwing away part. The lines that I threw off because this line got added now have to come back because I'm removing this line from my CHT. And that part is not at all obvious in a dynamic CHT. That how do you do that? In Lee-Chow, however, there are ways on how you can do that. I've shared like 2 locations where I found like good blog posts on how people do that. And like I already knew that this is possible in Lee-Chow, so that's why I wanted to be like that. That's another powerful addition on Lee-Chow, that you can actually support these things. Or you can go over these slides, or you can go over those blog posts in your own time. Additional problems, I'll just share these links. I mean, these are CF problems or whatever. So they are this one is a CF problem and this one is a coach F problem, but they're like, yeah, I think they have solutions. And I think this one at least has an editorial. This one might not have an editorial. So that's also useful just to see other scenarios where you can apply CHT. I think one of them is not even a DP question in itself, which is like an interesting thing. Like even for non-DP questions, you can use it. I'll just go over the TLDR at the end, which is basically you want your DP to look like this, generically speaking, that your DPI depends on some static AI thing, which is not even in the min recurrence, or you can move it out of the min recurrence because it's a static thing. And then you have a min or max over a j less than I, that is all candidates. And what you're doing generally is you're multiplying something which is a function of j, that is fj here, with gi, and then adding some hj. Here your hj becomes your c, your gi becomes your x, and your fj becomes your m. And that's how you get mx plus c. So that's that. Or you could have done the same thing with the max. That's how you're generically the DP structure that you're looking for. And yeah, I mean, we already discussed this technique, which was that if you have X's in a specific order, you could use sliding window. But if they're arbitrary, you have to do binary search. And these are all the blog posts. I think these are 2-3 problems which you'll find relevant. This is a Lee-Chow blog. This is a Yusako CHT blog. This is that quadratic algorithms like video, which is pretty good. And these are like typical blog posts on CHT. So yeah, I think that's all. If you guys have any questions, you can go ahead. Otherwise, we can end the session. I'll share the annotated version of this PDF, so basically with all these scribblings, if someone finds them useful, on the Discord channel later on. And I'll try to see if I can get the recording out also on YouTube, maybe by end of the day. Cool. Thanks a lot.